Hey guys, welcome to your second online lesson. As you can see, I have a nifty whiteboard now, so hopefully that'll make things a bit easier. Let's go ahead and jump into our second lesson. This is from section 5.3, lesson 5.3 from your textbook if you want to follow along in there. And we are going to continue to talk about triangles, but we're going to bring in the idea of congruence. I'm sure you guys remember that when we have two line segments, if we say that they're congruent, it means that they actually have the same measurements. So we took a ruler and we measured them. I have no idea what this is, but let's say. Then it would turn out that they had the same length. And you'll remember that from proofs, call this A, B, C, D. You remember from geometric proofs that I kept insisting on this annoying thing of saying that it's not the same thing exactly to say this as to say this. This refers to congruence, and this refers to the measurement of the segment. Now, in the case of line segments, they actually happen to end up meaning the same thing. Meaning, if two segments are congruent, then it means that they have the same measurement. And if they have the same measurement, it means that they're congruent. But when we bring in more complicated figures like triangles, it becomes a little more complicated. So let's see what it means for two triangles to be congruent. Okay, I did my best to make those look the same. Okay, so here we have two triangles, and if I were to say this, triangle ABC is congruent to triangle DEF. Now it's not exactly clear what that might mean, because with a segment it was easy because we only have one thing to measure, and that was the length of the segment. Now here we have lots of things to measure. We have three angles, we have three sides. So what might it mean for the two triangles to be congruent? Well, I'm sure you guessed it. It means that each part that corresponds to the other part is equal in measure. So that would mean that side AB is congruent to side DE. So I can say that. I'll put that right here. Segment AB is congruent to segment. I'm sure you can hear the kid crying outside. I don't know what's going on. Segment AB is congruent to segment DE. And of course that's true for the rest of the triangle. Okay. Now you'll see that I put this as a little double line. That just means that it's congruent to this, but not congruent to the others. Yeah. And what other part of the triangle could be congruent? Well, all we have left here is the angles. And that we're going to mark as congruent angles, just like that. Pretty easy, not too bad. And one interesting thing you'll notice is that if I look at this little thing I said here, this is what's called a congruence statement. It's stating that two triangles are congruent to one another. Now if I take a look at it, you'll see that the different parts in this statement actually correspond to each other. For example, you'll see that here I have AB, and here I have DE. And of course, side AB is congruent to side DE. You'll also see that, I'll do it like this, BC is in the same place as EF because they correspond to each other. These are called, and I'll write it down, corresponding parts. Right? And why do I say parts and not sides? Well, because angles can correspond too. For example, angle ABC corresponds to angle DEF, and so they are congruent. And you can see here ABC is in the same order as DEF. So the congruence statement alone, even if I didn't have the diagram, I could already say that segment AB is congruent to segment DE, and segment or side BC is congruent to EF, and FD is congruent to side CA. Right? And that's how I would do it with a diagram, and this is how I do it with a congruence statement. So you can see that I can't actually say, even though it would be correct to call this triangle EFD, there's nothing wrong with that as long as I go in order around the vertices. It's actually not right to say that triangle ABC is congruent to triangle EFD, because then it would look like the vertex E corresponds to vertex A, but as you can see, obviously it doesn't. A has a different measurement from E. Okay? So, just erase that a bit. So how could I figure out how to do one of these congruence statements? Right? Well, let's say I have a triangle like this, and I have a triangle, I'm going to try to do this the best I can, like this. Now, is it possible that these triangles are congruent? Well, they look pretty different, right? But if you think back to what it means for two triangles to be congruent, you can see that it doesn't really matter what position it's in. I could rotate it, right? Just like that. I could turn these. I could slide them around, right? I could even flip them. And it wouldn't actually change the fact that the angles and the sides are equal in both triangles. So for example, in this triangle, you can kind of see that this is the same as this, just rotated. For example, if I rotate it like this, well, it sure looks a lot like that original, well, somewhat, like that original triangle. So if I were going to mark this up with a showing which parts are congruent, you can see here, I could either, if I used a protractor, I could find that this angle is equal in measure to this angle. So, and pretty much by just looking at it, I can see that these are equal in measure. And I'm going to see that this angle is going to be congruent to this angle, and this angle is congruent to this angle, right? So that's pretty easy. Now, what about the sides? Well, I can see that this is the longest side, and it also happens to be opposite the longest angle, and that's an easy way to figure out which sides are congruent or correspond to one another, is by looking at the angles that are opposite. So this is the side that's angle opposite to that angle, so that's going to be congruent, and you can see it's also the longest side. And then this shorter side is also congruent, and then this other side, 1, 2, 3, right? And if I gave those names, actually let's use other letters. P, Q, S, U. How could I write this congruent statement? Well, remember, I can't just pick any order. I have to do it in the order of the parts that correspond. So I'm going to start with this triangle here on the left, and I will pick, I'll pick a vertex. It could be any of them, as long as they're in order when I write them out. And I'll say triangle PQR, right? The first one I don't have to worry about too much because I'm going to have to pay more attention when I write the second part of the statement. So triangle PQR. I have to look for which vertex corresponds to vertex P. Well, as you can see here, this is the angle that it is congruent to, so that's going to be U. And I have to write it that way. And then Q, you can see here, corresponds to T, so I'm going to have to put T here. And, of course, R corresponds to S. And so there's my congruence statement. Now, like I said before, the congruence statement also tells me something about the sides. Side PQ, side or segment PQ, let me look at the board here, corresponds to PQ, corresponds to UT. And QR corresponds to TS. And SU corresponds to RQ. SU, did I do that right? SU, excuse me, SURP, sorry, I said RQ. SU corresponds to RP, sorry. And there you go. So the congruence statement tells me a lot about the two triangles, and you should be able to look at two triangles and write a congruence statement just like that. Okay. And so, like we said before, it doesn't matter what position the triangle's in for the two triangles to be congruent. As long as all the angles and all of the sides are equal in length or equal in measure, then we're going to call the two triangles congruent. So like I said before, let me draw one like that. Okay, do my best to make them look similar. So if you look here, you'll see that I have a triangle that's actually flipped. Yeah? But is that actually going to change the angles or the measurement of the sides? No, it doesn't matter if I flip it or if I spin it, or I rotate it, or if I slide it. The angles and sides are going to remain the same length. So this is what's called a congruence transformation. Right here. Now, there are three basic kind of congruence transformations. This is called a flip, so that's pretty easy to remember. As you can see, it's been flipped. Or I could take this original triangle and I could rotate it. Yeah, so you can see I've taken this triangle here and I've rotated it. Don't ignore the fact that it's smaller. And this is just called a rotation, very simply. And of course, I can also slide it, and nothing's going to change. And that is simply called a slide, right? And so it should make sense to you that as long as we're not changing the length of the sides or the length of the angle or the measurement of the angles, it's still going to remain congruent. Okay? Let me erase that. All right. Let me just check that I've covered everything. Okay, one more thing. One thing you'll remember from just basic arithmetic is that we have certain properties that are kind of logical principles behind all the math that we do. For example, if I have a value a, that could be any number, let's say, it could be 3, something very obvious is that this is going to be equal to another value that's also equal to a. So it's equal to itself, right? And that seems really obvious, but it's one of those basic logical properties that's kind of behind all the math that we do. This, if you remember, is called the reflexive property. And another thing we've said before is that if I know that A is equal to B, right? If I know that, for example, John, let's say, if I know that John is Sally's sister, excuse me, John is Sally's brother, then I also know that Sally's brother is John, right? As long as she only has one brother. But similarly, if I know that one measurement is equal to another measurement, I can flip those around, and it doesn't really change anything to flip the position of them because the equality remains the same. And this, if you remember, is called the symmetric property. And finally, one of the most interesting for math is this. Right? If I know, for example, that segment AB is equal to 5 in measurement, and I know that 5 is the measurement of segment CD, then I'm going to know that AB is equal to CD in length. Or to put it kind of in easy human terms, if I know that, if you remember from logic, if I say Spot is a dog, dogs are canines, then Spot is a canine, right? That's sort of the logical expression of this math principle. Well, and this is called, if you remember, the transitive property. And that's one of the super, super important logical properties in math. Well, let's erase this. And this is also going to be true, since we're talking about triangles, it's going to be true for congruence with triangles, for example. And this is going to be extra helpful when we talk about proving that triangles are congruent. And yes, we're going to use geometric proofs to do that. For example, let's say triangle JKL is congruent to, reflexive, you guessed it, triangle JKL. Similarly down here with the symmetric property, triangle ABC, if triangle ABC is congruent to triangle DEF, then triangle DEF is congruent to triangle ABC. Okay? And with the transitive property, and this, like I said, is the most interesting of the three, if triangle ABC is congruent to triangle DEF, and triangle DEF is congruent to triangle triangle GHI, then what? What can you think? Yeah, triangle ABC is going to be congruent to triangle GHI. And that makes sense because when we talk about congruence, we're talking about measurements. So if I say all the measurements of triangle ABC are the same as triangle DEF, and all the measurements of triangle DEF are the same as GHI, then of course all of the measurements, the angles and the sides, are going to be equal to, in measure, to the measurements of triangle GHI. So hopefully that makes sense for you guys. That's the end of that lesson. What I'll do is I'll post a PDF along with this video, and I'd like you to do, on that PDF, I want you to do check for understanding, I want you to do number 2, 3, 4, 5, and let's see here, and I want you to do 8. Okay, just want you to do those 5 problems, bring them into class, and I'll give you a few points for them. Okay, all right, good luck. See you guys tomorrow.